We ended last time talking about scientific notation, how it takes away the guesswork for significant figures, because basically you just put all your significant figures to the left of the times table, 10 to the whatever, and you don't have to worry about the zero rules or anything. Just count every number there. They're all significant. The way we do scientific notation, so you want to put it in this format of the number being between 1 and 9.999, and then times 10 to some power. And if the power of 10 is positive, that means the number is huge, much, much larger than 1. And if the power of 10 is negative, that means the number is very small. It's representing a number that's between 0 and 1, like 0.0006 or something. And the exponent is going to tell you how many places to move. So if we have a number like this, which is officially 50,620,000, the first thing you want to do is move the decimal. So here's your decimal, and you want to move it until there's only one non-zero digit to the left. So currently with this decimal, we have 3 non-zero digits to the left. As we move it around, right here is where only one non-zero digit would be to the left, the 5. So then we write that number down, 5.062, and now we need to multiply it by 10 for all those jumps we just made. And each jump is a power of 10. In this case, it's going to be positive because our initial number was so large. So because this is such a large number, we want a power of 10 that's positive. And since we made 7 jumps, that would be 10 to the 7th. So in scientific notation, it's 5.062 times 10 to the 7th. If there's a number between 0 and 1, right? That's what this number is. Then same thing occurs. You're going to move the decimal until only one number, one non-zero digit is to the left. So we got to move this decimal over this way to right here so that it's between the 4 and the 8, and only the 4 would be the non-zero number to the left of the decimal. So we start with 4.87, and now we have to multiply that by 10 to some power to compensate for all the jumps we just did with our decimal. And since it was 5 jumps, we're going to put 10 to the negative 5 negative because the 0 to 1 thing was happening here. That's a very small number that we started with. If you would like more practice, I've posted this on the webpage. You can practice with Khan Academy and doing more of these. All right, now on your calculator, there's a button. Sometimes it has an EXP on it. Sometimes it has an EE on it. Many calculators are unfortunately different in this regard. If you have one of the ones that the math department says, I think there's like a comma, and above that is an EE, and it's in blue, so you would have to hit the second function, which is in blue. And then that'll turn the blue EE if you have that graphing calculator. Anyway, what these things mean is times 10 to the. So if we were trying to write a number like 6.02 times 10 to the 23rd into our calculator, we would hit the 6.02, then we hit that EXP or EE button, and then we just put what the power of 10 would be. So that button means times 10 to the, so 6.02 times 10 to the, and then positive 23. If we had 5.31 times 10 to the negative 7, we're trying to put that in the calculator. 5.31, you hit your EE or EXP button, which means times 10 to the, and then negative 7. Now, sometimes for that negative, you want to hit that plus minus button. That's usually down by the 0, right? And then there's like a 1, 2, 3 like this. Usually it's down there. On the Google one, let me show you that. On the Google one, play some music while I'm doing this. On the Google one, important to use random capitalization. All right, 5.31 E, so 5.31 exponent. So there is no plus minus, so you just hit the minus here, 7. So that's what that is. Okay, and then for some reason they make it lowercase. Don't ask me why these things happen. I don't know why we do that. But anyway, moving on. Why? Why did I go through all that? Well, hitting those numbers will allow the calculator to realize when you're using scientific notation that the whole number is connected as opposed to two separate statements. So if, for example, you're trying to divide 9.3 times 10 to the 11th by 4.1 times 10 to the third, you hopefully remember from math that when you divide powers of 10, so we're doing 10 to the 11th divided by 10 to the third, you subtract the exponents. So it should equal something in the ballpark of 10 to the 8th. However, if you put that into the calculator using the caret or, what we call the caret, this little raised, or basically not the EXP button, then the calculator is going to give you this answer. And the reason it gives you that answer is because it takes that 9.3 times 10 to the 11th, it divides by the 4.1, but then it doesn't know that that times 10 to the third is connected to that 4.1, so it brings the times 10 to the third back into the numerator. And that's why you see the 14, because now you add exponents when you multiply, right? And you get 10 to the 14th. So to avoid that, you will either want to use the EXP or EE button, or if you really like your caret button, then make sure you put things in parentheses so that the calculator knows this is one whole statement. It's not two parts, the 4.1 and the times 10 to the third, so it doesn't break it up when it's trying to do the division. Okay. So calculating with significant figures, hopefully you've heard the term that a chain is as strong as the weakest link. The weakest link is, in this case, a paper clip. So if you're trying to use a chain to get something out of a ditch and you had one of the chain links was a paper clip, it of course would not work because that's the weakest link. Likewise, as we've just learned that numbers imply the quality of the measurement that has been done, if you multiply 12.51 meters by 0.0524 meters, you would get this number on your calculator. Now, the problem is this number has 4 significant figures, and this number has 3 significant figures, and now this number has 1, 2, 3, 4, 6. So 6 is certainly a higher quality than anything that went into making that 6. And that makes us unhappy as scientists. So if we have this and write this down as our answer, we're kind of lying because we're assuming that just because we took something that was only good to 4 and something that was only good to 3 would miraculously do a 6 significant figure measurement now just because we multiplied them. So that should not be the case. What we want to do is round this number. So we want to round it to whatever the least number of significant figures was that made it up. And since 3 is the lower of those two numbers, we want to make sure this has 3 significant figures. All right. Hopefully that makes sense. So this now reflects the weakest of the links that made up that number. Same's true with division. Oh, by the way, this should be meters times meters is meters squared, by the way. Okay. With division, same rules apply. This number here has 4. This number here has 2. You put it on a calculator, you get 7 significant figures. Okay. And you can't have a 7 significant figure number when you put a 4 and a 2 in there. This is like, getting something fancy. I was going to say pate, but really, who of us has eaten pate? Angus beef from this hot dogs, basically. So you can't get that to happen. So you have to have this reflect what went in. And so what went in had 2 significant figures. So you're going to round this number down to 2 significant figures. And again, liters would cancel here. So there'd be no units. Anyway, we'll talk about that next. So, as Mufasa would tell you, remember 2 things. Numbers communicate the quality of the measurement. So that's why we can't have these really long numbers with lots of significant digits when we do just a calculator arithmetic, because it's implying that the number is a higher quality than it should be. And also keep your magnitude when you're rounding. So when I multiplied 2638, which has 4 significant digits, and 25, which has 2, the answer I get, I want it to be, I think it's 65,950. I want to round it to two significant figures, but I can't just say 66, because if I owed someone $65,950 and I paid them 66, that is not the same magnitude. That is not the same uh, amount. So you have to make sure you maintain the size of the number, and the size of the number needs to be in the tens of thousands. So you would put these insignificant zeros behind that 66 so that it says 66,000. Okay. Here's some more examples. So if I'm going to multiply 5.880, which is times 10.4, you get 61,152. But that has 5 significant digits. This had 3, this had 4. So we want to make sure we round this to 3 significant digits. So we would say 61.2, right? Because you round up with 5 anyway. All right. So then 29.5 divided by 0.082 is 359.756098. Again, lots of numbers. Not that this had 3, this had 2. So we want to make sure this has 2. So if we rounded that to 2 significant digits, we don't want to just say 36, because if someone was owed $359, $36 would not make it happen. But it's true that when you round that, it would be 36 plus that 0 to make sure you keep the magnitude. So 360 is what we would round it to. Okay, so you can live your whole life without doing some addition, subtraction, and significant figures, but we're going to teach it to you anyway. Significant figures with addition and subtraction is slightly different. You line everything up with the decimals, you add or subtract, and then you make sure that your answer is cut off at wherever your significant figures ended in your two add-ins. So 5.44 stopped in the tenths, 2.6103 stopped in the 10,000ths, but 10,000ths wasn't true here, and thousandths wasn't true here, so we have to stop at the hundredths. So you round the number to wherever your inputs had the least significant figure. So I used to do a lab where you fill like a beaker, which only has like hash marks on the 50, and then you try to put it into a graduated cylinder that has hash marks on the 1. And you will see that if you keep adding this, you're not anywhere close because you don't really know anything here. So this is what it's basically trying to tell you. Like, if the best you know is tens, then you won't know ones when you add them all together. You'll only know things within 10. I don't know if that helped, but gave me more airtime. So same thing here. This number is only good to the tens. This number is good to the tenths. So you do the operation, but then you have to round to the tens place because this is not a significant 0. So the last significant number for this contributor was in the tens place. So your answer is there. All right. So I was told that you don't have to remember these rules because it's going to be open book because we're online. But if you ever did, remember, if you put the plus and the minus together, it sort of makes one of these charts, right? And if you put the multiplication and division together, then you don't make one of those charts. You make something that I was told looks like a circus guy standing on his head with no arms, though it's occurring to me. Or, as I said, something you'd see on the wall in a horror film because there's some spirit there. All right, there it is. I heard my mic went off today, so now you can hear it in all its melodious term. I hope that was helpful.